implement single area OSPF version 2. This is the topology. Okay, complete this topology. I will do it on Packet Tracer. I will use Packet Tracer A2. Okay, it use 4321 router for R1. (2960) switch is A1, and 3650 switches for D1 and D2. 3650. Now I use these straight through cables from gigabit 001 on router to 2960 switch fast Ethernet 11. Okay, this from R1 gigabit 001 to switch fast Ethernet 11. From D1 interface 5 to fast Ethernet 1. From D1 105 to fast Ethernet 1. From 5 on D2 to fast Ethernet 3. On D2 5 and fast Ethernet 3 on 2960 switch. PCs, PC1, PC2, PC3, and PC4. Okay, the PC is connected to ports 23 and 24 on D1 and on D2. Okay, from 23 to PC1, 24, PC2, 23, PC3, 24, PC4. Okay, I will use labels like this topology. Okay, very good. Okay, very nice. the addressing table R1 with one physical interface and two loopback interfaces, D1 with three networks and three physical interfaces, D2 also with three networks and three physical interfaces, four PCs. You will configure single area OSPF version 2 for IPv4 and a multi-access Ethernet LAN. Okay, this is a multi-access Ethernet LAN. Okay, because there is a switch in the middle of three routers. This lab was specifically designed to use two layer 3 switches instead of three routers to highlight how a layer 3 switch can also be used to provide routing services. This lab is an exercise in developing, deploying, and verifying how OSPF operates and does not reflect networking best practices. The router used with CCNP hands-on lab is a Cisco 4221, and the two layer 3 switches are Catalyst 3560 switches. Other layer 3 switches and Cisco iOS versions can be used. Depending on the model and Cisco iOS versions, the commands available and the output produced may vary from what is shown in the lab. Make sure that the switches have been erased and have no startup configurations. If you are unsure, contact your instructor. On Packet Tracer, all devices do not have configurations. Otherwise, erase the startup config on devices and reload them. Required resources: one router, Cisco 4221. I'm using 4321. Two switches, Cisco 3650. One switch, Cisco 2960. Four PCs. Console cables, Ethernet cables. Build the network and configure basic device settings and interface addressing. The layer 2 switch should only have a default configuration. Cable the network. Ready. Configure basic settings for the router and the two layer 3 switches. Console into each router and layer 3 switch. Enter global configuration mode and apply the basic settings and interface addressing using the following startup configurations for each device. Okay, this is for router R1. This is for switch D1 and switch D2. To be sure, I will copy all this to a notepad and paste. Okay, router R1. Hostname, no IP domain lookup, line console configuration, loopback 0, loopback 1, gigabit 001, very nice, IP address. Okay, copy this to the router. Copy. R1, command line interface. No enable configure terminal. Paste. Okay, verify, no errors. Very good. Enter. Okay, for D1, hostname, no IP domain lookup, configuration of console, layer 3 interface with no switch port, gigabit 5, IP address, 23 and 24 with IP addresses and no switch port, layer 3 interfaces. Okay, copy, go to D1 on physical interface, place the power supply, go to command line interface, wait a moment for the boot, enter no enable configure terminal, paste, verify no errors, no issues, very good. Now D2, basically the same configuration but with different networks, different IP addresses. Copy D2, physical interface, place the power supply, command line interface, enter no enable configure terminal, paste. Okay, very good. Okay, save the running configuration to startup config. Okay, on R1 and copy running config to startup config. Enter. Okay, copy this D1 and paste. Enter. D2 and paste. Enter. Verify the interface status using the show IP interface brief command. Okay, 3 interfaces on the devices with three IP addresses. R1 show IP interface brief pipe include manual. Okay, three interfaces, 3 IP addresses, state up, protocol up. Okay, copy this for D1 and D2, paste, enter. Very good, 3 IP addresses up. D2, enter. Very nice, 3 IP addresses, 3 interfaces, up. Verify direct connectivity between the highlighted IP addresses of R1, D1, and D2. Okay, from R1 ping 10.10.02 and 10.10.03. Okay, from R1 ping this IP 10.10.02 and 10.10.03. Ping 10.10.02. Success and 10.10.03. Okay, very good. All 3 devices should be able to reach the other directly connected networks. Troubleshoot if necessary. Configure single area OSPF version 2. You will implement single area OSPF on a multi-access Ethernet network. OSPF can be enabled using the traditional network router config command and wildcard mask. The wildcard mask enables the configuration to be as specific or vague as necessary. Okay, network and IP address with wildcard mask 000 area. This configuring the network statement with an IP address explicitly enables OSPF of that interface. Network address wildcard mask area. The wildcard mask can explicitly match a subnet, or it can be less specific to match several subnets as required. The network 000 and wildcard mask 255, 255, 255, 255, and area. This is the vaguest method, as the 000 network with 255, 255, 255, 255 wildcard mask matches all enabled interfaces. An alternate method to using the network router configuration command is to use the interface specific method. Instead of the network statement, an interface is enabled for OSPF using the IP OSPF and process ID and area interface configuration command. Although simpler to use, the disadvantage is that the configuration is not centralized and increases in complexity as the number of interfaces on the routers increases. There is a newer method to configure OSPF using address families. Address families are covered in OSPF version 3 and in CCNP Enterprise Advanced Routing. Implement OSPF of D1 using explicit IP address. D1 will advertise its OSPF networks using OSPF network IP address 000 wildcard and area. This method uses quad 0 wildcard mask. This enables OSPF for area 0 only on the interfaces that explicitly match the IP address configured. Layer 3 switches are not enabled to perform routing by default. Therefore, routing must be enabled using the IP routing global configuration command. Okay, do this on D1 IP routing. Okay, on D1, configure terminal IP routing. Enter the OSPF router configuration mode using process ID 123. Okay, on D1, router OSPF 123. I'm sorry, OSPF. Very nice, you are on router configuration mode. When using the quad 0 method, it is not necessary to calculate the actual wildcard mask. You simply advertise the IP address of the interface with a quad 0 wildcard mask, and OSPF will advertise using the subnet mask of the interface. Configure OSPF to advertise the network address of the gigabit 5 interface, that is 10.10.02, with the quad 0 mask. Okay, on D1. And you can do the following for help. Do and copy this. Do show IP interface brief pipe include manual enter 5 interface 5 using this IP. So use network, the IP address, no network address. This is IP address, it's a host address. 10.10.02 wildcard mask for a specific interface, and the area is 0. Okay, the area is 0 for all the network. Enter. Now configure 23 and 24 interfaces using the quad 0 mask. Okay, this and this another. A1 quad 0 wildcard mask area 0, and 9191 quad 0 mask area 0. Ready? These networks are now being advertised to other OSPF routers. Verify the OSPF configuration on D1. Show IP protocols. Okay, and show IP protocols. Okay, you can see the process ID 123, the router ID 10.10.91 is the highest active IP address on the router. The highest IP address on the router will be assigned, in this case for router ID for OSPF. Okay, the three networks, the advertised networks with Quad0 wildcard mask for a specific interface. Very nice. The OSPF router ID chosen was the highest active IP before address configured on D1. The routing for network section in the output above confirms that the configured statements are accurately advertising the D1 networks. Implement OSPF on D2 using wildcard masks. D2 will advertise its OSPF networks using the network router configuration command and wildcard masks. Like D1, D2 must be enabled for routing and IP routing. On D2, configure terminal IP routing. The process ID 123. Note that process ID are only locally significant. Therefore, the process ID of other OSPF routers do not need to match. However, using the same process ID makes it simpler to remember and reduces potential configuration mistakes. The same process ID, but router OSPF 123 do not need to match, but use 123. Go to D2, router OSPF 123, enter. Configure D2 to advertise the gigabit 5 interface with 29 prefix and area 0. The wildcard mask can be calculated by deducting the subnet mask from 255, 255, 255, 255, resulting in a wildcard mask of 0007. How to calculate the wildcard mask is very easy. 255 minus 255 is 0. 255 minus 255 is 0. 255 minus 255 is 0. 255 minus 248 is 7. This is the wildcard mask. Very nice. And add that network. But you can do the following: do show IP route connected. And now you can see this is for gigabit 5. For gigabit 5. And the prefix is 29. So use network. Use this network address, in this case network address wildcard. For 29 is 7 in area 0. Very nice. Now you will see this message. Notice the informational message confirming that D2 has established a neighbor relationship with D1. OSPF adjacency, process ID 123. The neighbor is 10.10.9.1. Remember, on D1, the router ID is 10.10.9.1. So D2 establishes an adjacency with D1. Remember, this A1 switch is a layer 2 switch. On gigabit 5, on this interface, gigabit 5. Very nice. And next, configure D2 to advertise the two prefix 24 networks and area 0. Now configure this. Okay, these two networks. Okay, network 10.10.24.0. The wildcard for 24 is 255. Okay, 255 minus 0 is 255. Area 0. Okay, look at the wildcard mask for 24 prefix. Okay, enter, and the next 10.10.25.0. 10.10.25.0, the same wildcard mask and area 0. Enter, very nice. The two networks could also be enabled using the network 10.10.24.0.0.254.255 statement instead. There are no informational messages this time because these interfaces are not connected to other OSPF-enabled routers. However, these networks are now being advertised to other OSPF routers. Okay, no neighbors, no routers on this side. So there are no informational messages. Okay, show IP protocols and show IP protocols. Okay, OSPF123, process ID, router ID, the highest active IP address 10.10.25.1. Okay. The advertised networks, and the gateway is 10.10.9.1. Again, the OSPF router ID choosing was the highest active IPv4 address configured on D2. The routing for network section confirms that the configured statements are accurately advertising the D2 networks. We also have another routing information source 10.10.9.1. Okay, so 10.10.9.1 is the router ID of R1, the router ID of R1. Okay, is a source of OSPF information. Implement OSPF on R1 using the interface specific method. R1 will use the OSPF interface specific method to advertise the loopback1 interface and the gigabit 001 interface. Interface loopback 0 will be advertised in part 3. The interface specific method is simple because there is no need to enter network statements or calculate wildcard masks. You simply enter the IP OSPF process ID area interface configuration command on an interface. Alternatively, the network 0000, 255, area 0 router configuration command would be simpler. However, it would be enable OSPF on all interfaces including the loopback 0 interface that will be advertised in part 3. The loopback interface on R1 is only configured to simulate another network for OSPF to advertise. However, the default behavior of OSPF for loopback interfaces is to advertise a 32-bit host route. To ensure that the 26 network prefix is advertised, the IP OSPF network point-to-point interface command must be configured on the loopback1 interface. Okay. On this loopback1 interface. I will advertise the internet network later. Now, configure this loopback1 point-to-point. Okay. Change the network type of the loopback interfaces so that they are advertised with the correct subnet. Okay, loopback1 IP OSPF network point-to-point. To avoid the 32-bit host route and to ensure that the 26 prefix is advertised. Okay, go to R1, configure terminal, loopback interface, loopback1. IP OSPF network point dash to dash point. Enter. Next, enable the loopback interface for OSPF using IP OSPF 123.80 command. IP OSPF 123.80. Enter. Enter interface gigabit 001. Okay, and enabled for OSPF. Okay, this another interface gigabit 001. Interface gigabit 001. IP OSPF 123.80. Enter. And now you can see the adjacencies. This is the adjacency with D2. So 10.10.25.1 is the router ID of D2. Okay, 10.10.25.1. And the adjacency with D1, that is 10.10.91. D1 router ID 10.10.91. Very nice. Notice how the informational messages are confirming that the neighbor adjacencies have been established with D1 and D2. Verify. Show IP protocols pipes section OSPF. Okay, go to R1. Show IP protocols pipe section OSPF. Okay, don't worry about this. This is not supported by Packet Tracer, so only use show IP protocols. And you can see the process ID 123, the router ID, the highest active IP address. So the highest active IP address is loopback 0. Routing sources D1 and D2. Sources of OSPF information. This is R1 itself. Okay, and also you can see the routing networks loopback 1 and gigabit 001 configured explicitly for area 0. The router ID choosing is the highest active IP4 loopback address configured on R1. The routing for network section confirms that the routing was explicitly configured on the interfaces. It also displays a new routing source, D2. Assign router IDs on R1, D1, and D2. The OSPF router ID is dynamically assigned in order of preference. Manually configured using the router ID command. If it is not manually assigned, then the highest enabled loopback IP address is used as the router ID. If there are no loopback interfaces configured, then the highest IP address of any active physical interfaces in the app state becomes the router ID when the OSPF process initializes. It is best to assign a static OSPF router ID for troubleshooting purposes. To force an existing OSPF network to use the new router IP, the OSPF process must be reset using the clear IP OSPF process privilege exec command. Okay, for R1, use router ID 1111 and in clear IP OSPF process. Okay, go to R1, configure terminal, router OSPF123 router dash ID 1111 enter and reset the OSPF process clear IP OSPF process enter yes. Very nice. Okay, the adjacencies with D1 and D2 down, but now loading full with D2 and D1. Verify show IP protocols. Now this is the router ID 1111. Repeat the process on D1 and D2. Use router ID 2222 and 3333. Okay, 2 for D1 and 3 for D2. Okay, and verify. Okay, go to D1, configure terminal, router OSPF123, router ID 2222, and clear IP OSPF process. Yes. Verify show IP protocols. 2222. Okay, very nice. And D2. Configure terminal, router OSPF123, router ID 3333, and clear IP OSPF process. Yes. Verify show IP protocols. Router ID 3333. Very good. And verify OSPF settings on R1, D1, and D2. It is imperative to know how to validate that OSPF is operating as configured. The show running config command only displays the initial OSPF configuration. It does not validate the operation and functionality of OSPF. Along with the show IP protocols command, there are several other useful OSPF-related show commands to verify that OSPF is operating as expected. Show IP root OSPF privilege exit command is used to verify the operation of OSPF. The command displays OSPF routes learned with an O, the administrative distance, the assigned metric, the NetHub IP address, and the local exit interface to reach the network. Okay, show IP route OSPF pipe begin gateway. On R1, show IP route OSPF pipe begin gateway, case sensitive G uppercase gateway. Okay, show IP route, sorry, this is route, enter. Okay, use only show IP route OSPF. Very nice. 4 networks, okay, remote networks, not including directly connected networks. For R1, the directly connected networks are this network 192.168.1.0 and this network 10.10.0.0. Okay, these are directly connected networks. But the OSPF remote networks are 80, 90, 24.0 and 25.0. 80, 90, 24.0 and 25.0 remote OSPF networks. So this is very good. Okay, do the same process on D1 and D2. Okay, copy show IP route OSPF. D1, paste, enter. 3 remote networks 24/0, 25/0, and 192.168.1.0. For D1, remote networks 24/0, 25/0, and 192.168.1.0. Very good. And for D2, shape root OSPF 80, 90, and 192.168.1.0. Okay, the remote OSPF networks. Okay, for D2, 80, 90, and 192.168.1.0. Very good. Okay, but go to R1 and don't forget this. OSPF roots learned with an O. O. The administrative distance. Administrative distance 110. Metric. NetHop IP address. And local exit interface to reach the network. Okay, remember R1. Okay, R1 OSPF network 10.10.80. R1 OSPF network 10.10.80. The exit interface on R1 is gigabit 001. The exit interface is gigabit 001. And how to reach 10.10.80? You will use 10.10.02. 10.10.02. And to reach 10.10.24, gigabit 001 and use 10.10.03. And on R1 to reach 10.10.24.0, use interface gigabit 001 and use NetHop IP number 3. NetHop IP number 3. Use show IP OSPF interface brief command to verify which interfaces are enabled for OSPF. Process ID, area ID, and state. A missing interface could be the result of an incorrect network statement, IP addressing problem, or disabled interface. Okay. Show IP OSPF interface brief. R1. Show IP OSPF interface brief. Enter. Okay, on R1, 2 interfaces, loopback 0, very nice, process ID, 123 area, IP address, and mask on the interface. Okay, very nice. Okay, the state. 2 interfaces, show IP OSPF interface brief, copy this, D1, paste, enter. Okay, 3 interfaces, very good. Interface, process ID, the area is 0, IP address and subnet mask, very nice. The cost, the state, we'll see next step what means what is BDR or DR or okay. D2 show IP OSPF interface brief. 3 interfaces, state DR in this case. 3 interface, very nice. Omitting the brief keyword displays detailed information about the OSPF enabled interfaces. This state field defines the state of the link and can be DR. This is the designated router on multi-access network. Ethernet network. Okay, this Ethernet network, because in the middle there is a switch to which this interface is connected. The DR establishes OSPF adjacencies with all other routers on the network. VDR. This is the backup designated router on the multi-access network to which this interface is connected. Like the DR, the VDR establishes adjacencies with all other routers on the broadcast network. DR other. This is a DR other. It is neither the DR or the VDR on the multi-access network. All known DRs and VDRs on the broadcast network would be DR others and establish adjacencies only with the DR and the VDR. Point-to-point. This is an OSPF point-to-point interface and does not require a DR or VDR. In this state, the interface is fully functional and starts exchanging hello packets with all of its neighbors. Okay, for example, go to R1. Loopback 0 is point-to-point, and gigabit DR other. On D1, gigabit 5 is BDR and other interfaces DR. And D2, all interfaces DR. And this may vary. Okay, don't worry if you have different results. Okay, and verify that on the multi-access network, R1 is using interface gigabit 001. D1 is using interface gigabit 5, and D2 also gigabit 5. On R1, gigabit 001 is DR other. On D1, gigabit 5 is BDR. And on D2, gigabit 5 is DR. So on the multi-access network should be only one DR, only one BDR, and other connected routers should be DR other. So that's why there is only one DR, the designated router, only one BDR, the backup designated router, and only one DR other. Very nice. Okay, and remember, can be more DR other routers. Use the show IP OSPF neighbor detail command to verify which OSPF neighbor your device has established adjacencies with, the state, the netscope IP address, and the exit interface to use. A neighbor may not be appearing include router IDs that are not unique, connecting interfaces that are not on a common subnet, MTU values that do not match, area ID that is not correct, hello and dead interval timers that do not match, or authentication type credentials that do not match. The following outputs confirms that our devices have correctly established adjacencies. The output for R1 is shown below. Repeat the command for D1 and D2. Show IP OSPF neighbor. R1. Show IP OSPF neighbor. Enter. Okay, for R1, the neighbors are D1 and D2. D1 is the backup designated router, and D2 is the designated router. Okay, this is the state IP address on the neighbor. In this case, for D2 is number 3. For D2 is number 3. For D1 number 2. For D1 number 2. Okay, the IP on the neighbor, and the exit interface, and the local exit interface gigabit 001. Gigabit 001. Okay, and do this on D1 and D2. Okay, and copy this show IP OSPF neighbor D1, paste, enter. Okay, this is D2 and R1. D2 is the designated router, R1 DR other. Okay, D2 paste show IP OSPF neighbor. R1 is other, DR other, and D1 is backup designated router. Very good. Other OSPF validation commands include the show IP OSPF, show IP OSPF topology info, show IP OSPF database commands. Use these commands now and identify what types of information they generate, which may be useful to know when they're troubleshooting a network. Okay, for example, show IP OSPF. Okay, go to R1. Show IP OSPF. You can see the process ID, router ID. Okay, LSA is link state advertisements. Okay, information about LSA. Also, you can use show IP OSPF topology-info. Enter. Okay, this command is not supported on Packet Tracer, and you can use show IP OSPF database. This is very good, and the router link states for area 0. Okay, remember this is R1. The link ID. Okay, this was D1, this was R1, this was D2, but now this is R1, this is D1, this is D2. And netlink states this is D2. Configure and verify the advertising of a default route. You will configure a default static route to the internet on R1. R1 will then propagate the default route to other OSPF routers as an external type 2 OSPF route, OE2. Propagating a default is the most efficient method to provide a consistent default gateway to all OSPF-enabled devices. Configure the default route advertisement on R1. R1 will be the gateway of last resort for the OSPF internetwork. In our sample topology, the internet is simulated using the loopback 0 interface. Configure a static default route out of the loopback 0 interface on R1. The IP route. Exit interface loopback 0. Okay, to reach internet, use loopback 0. On R1, configure terminal IP route 0000. This is the default static route, and the exit interface is loopback 0. Don't worry about this message. Okay, do this on R1. Disregard the informational message. In a production environment, a valid physical interface would be used to provide default gateway services. Enter OSPF router configuration mode and use the default information originate command to enable default route propagation. The always keyword advertises a default route even if a static default route does not exist, while the route metric and metric type can be changed. Arwing is configured to propagate the default route. Okay, propagate. Go to R1. Router OSPF123. Default dash information space originate. Enter. And okay, and verify with show IP route static. Show IP route static. Okay, static. The default static route directly connected. Exit interface loopback 0. Verify the routing table on D1 and D2. Show IP route. Include gateway 00 on D1 and on D2. D1 show IP route pipe include okay, case sensitive G uppercase gateway pipe 0/0. Enter. The gateway of last resort is 10.10.01 to network quad 0 internet. Okay, for D1 the last resort is 10.10.01 to reach internet. Okay, OSPF external type 2. This is quad 0 internet. The administrative distance, the metric, the last resort, exit interface 5. For D1, exit interface gigabit 5, and last resort 10.10.01. Okay, the same command on D2. Enter. Last resort 10.10.01 to reach internet. Okay, and the last resort exit interface also 5. Also 5. Implement OSPF network optimizing features. You will configure OSPF optimizing features including passive interfaces, link costs, reference bandwidth, hello and dead intervals, timers. Configure passive interfaces on R1, D1, and D2. A passive interface does not send out OSPF messages or process any received OSPF packets. However, the passive interface network segment is still added to the link state database (LSDB) and advertised out of non-passive interfaces. For security reasons, LAN interfaces which are not connected to other OSPF routers should be passive. There are two approaches to identify passive interfaces. Use the passive interface router configuration command to make an interface passive. This is a good approach to use when there are only a few interfaces to make passive. Use the passive interface default router configuration command to make all interfaces passive, and then make some interfaces not passive using the no passive interface ID command. This is a good approach to use when there are many interfaces to make passive, but only a few interfaces that should be not passive. R1 only needs the loopback 1 interface to be passive. The first approach is used to make the loopback one interface passive. Okay, enter the OSPF router configuration modes and passive loopback one. Okay, gigabit 001 should not be passive because there are neighbors, there are OSPF neighbors, and loopback one should be passive. Configure terminal router OSPF 123 passive dash interface loopback one enter. Okay, end. And verify show IP protocols section OSPF. Using show IP protocols. Now you can see passive interface loopback one. A layer 3 switch can potentially have many interfaces that should be passive. For example, assume that D1 and D2 only require their gigabit 5 interface to not be passive. However, all other interfaces should be passive. Using the first approach would be very time consuming. For this reason, the second approach will be used. All active interfaces will be rendered passive and only interface 5 will be re-enabled. Okay, passive interface default and no passive interface 5. Okay, on D1, go D1, configure terminal router OSPF123 passive dash interface default. Enter all. Okay, all interfaces are passive, but no passive interface gigabit 10105. This 105. Enter. Okay, end. Wait a moment and you will see the adjacencies with R1 and D2. Very nice. Notice the information messages stating that the OSPF adjacency with R1 and D2 transitioned to the down state. Disabling the passive feature on interface 5 re-enable the OSPF adjacency. Repeat the process on D2. Okay, go to D2, configure terminal router OSPF123 OSPF123 passive dash interface default, no passive interface gigabit 105 at. Okay, wait a moment. Okay, adjacency is re-established. Adjust OSPF link costs. The OSPF path metric is based on the cumulative interface cost to the network. OSPF assigns the OSPF link cost using the formula. The cost is equal reference bandwidth by interface bandwidth. The default reference bandwidth is 100 megabits per second. Therefore, the default formula is cost is equal 100 million 100 megabits per second by interface bandwidth. For example, a fast Ethernet interface would be assigned a cost of 100 million by 100 million is 1. The default reference bandwidth does not differentiate interfaces faster than Fast Ethernet. Therefore, OSPF assigns the identical cost of 1 to Fast Ethernet, Gigabit Ethernet, and 10 Gigabit Ethernet interfaces. OSPF makes no distinction that the Gigabit and 10 Gigabit interfaces are faster. Okay, and for example, because 100 million by 1000 million will be equal to 0.1. Remember, this is the interface bandwidth, and this is the reference bandwidth. So the result for gigabit interface will be 0.1. And for OSPF, this will be rounded to 1. Okay, to 1. So that's why OSPF assigns the identical cost for Fast Ethernet, Gigabit Ethernet, and 10 Gigabit Ethernet interfaces. Use the autocode reference bandwidth router configuration command to change the reference bandwidth as follows. If autocode reference bandwidth is 100, assign the default reference bandwidth to 100 megabits per second, which is the default setting. With this setting, Fast Ethernet is 1, Gigabit is 1, and 10 Gigabit is 1. If autocode reference bandwidth is 1000, assign the default reference bandwidth to 1 Gigabit per second. Fast Ethernet is 10, Gigabit 1, and 10 Gigabit 1. With autocode reference bandwidth of 10,000, assign the default reference bandwidth to 10 gigabits per second. Fast Ethernet 100, Gigabit 10, and 10 Gigabit is 1. The autocode reference bandwidth must be the same on all routers in the area. Otherwise, suboptimal routing may occur. On R1, change the reference bandwidth to account for the gigabit interfaces. Okay, so set to 1000. That means 1000 means 1 gigabit per second. Okay. Go to R1, configure terminal, router OSPF123, auto cost reference bandwidth 1000. Okay, don't worry about this message. Ensure reference bandwidth is consistent across all routers and okay, verify. Show IP OSPF include reference. Show IP OSPF pipe include case sensitive R uppercase reference enter. Okay, Packet Tracer does not support this pipe, only show IP OSPF enter. No autoghost reference bandwidth here, so okay, but on a real device the reference bandwidth is 1000 megabits per second. Repeat the steps on D1 and D2. Okay, and go to D1. D1. Configure terminal, router OSPF123, auto code reference, bandwidth 1000, and Okay, and copy this. And D2, configure terminal router OSPF123. Paste, enter, and okay, very nice. And verify on verify the routing table on D2 to see if the route metrics have increased. Okay, show IP route OSPF on R1, D1, and D2. Okay, and note the metric is 20. Okay, go to R1. R1, show IP route OSPF. Okay, the metric is 20. Before was 2, as you can see. Okay, why 20? Okay, you are on R1, and the OSPF route 10.10.80, 10.10.80. Okay, the cost, the metric is the cost. The cost is 20. Okay, 10 here. Cost 10. Okay, for this link, and cost 10 for this another link. Okay, 10 plus 10 is 20. Okay, on D1, show IP route OSPF. Okay, 20, 20, 10, and 1. Okay, the propagated default static route uses 1 by default. A lower metric, okay, a lower cost. Okay, to reach 24.0 and 25.0 is 20. Okay, this is the one, and to reach 24.0, 10 plus 10 is 20. Okay, 10 plus 10 is 20. Okay, and to reach 192.168.10, 10. To reach 192.168.10, 10. Okay, this is a loopback. Only 10. The same way on D2. Alter hello and dead intervals timers. OSPF hello messages are exchanged to establish a neighbor relationship and to ensure that adjacent OSPF neighbors are still available. OSPF uses a hello timer and dead interval timer, which is 4 times the hello timer. When a router receives a hello packet, the dead interval resets and starts to decrement again. If subsequent hello packets are not received before the OSPF that interval timer reaches 0, the neighbor state is changed to down. The router then sends out the appropriate topology change, LSAT, link state advertisement to all other peers, and the SPF algorithm must be recalculated on all routers in the area. Okay, SPF is shorted path first. Okay, the default OSPF hello timer intervals varies based on the OSPF network type. On broadcast and point-to-point links, the default hello timer interval is 10 seconds and that timer interval is 40 seconds. On non-broadcast multi-access MBA, MA, and point-to-multipoint networks, the default hello interval is 30 seconds with a dead timer interval of 120 seconds. You can alter the hello timer interval values between 1 and 65,535 seconds using the IPOSPF hello interval interface configuration command. The dead interval can be modified using the IPOSPF dead interval sequence interface configuration command. However, the command is really not required because changing the hello timer interval automatically modifies the default dead interval. On R1, change the hello interval on gigabit 001 interface to 5 seconds and dead interval time to 20 seconds. Okay, on R1. Okay, by default is 10 and 40, but change to 5 and 20. Okay, go to R1, configure terminal interface gigabit 001. IP OSPF hello dash interval 5 and that interval 20 and notice how R1 has received OSPF adjacency change messages for D1 and D2. The reason is because OSPF timers must match between interconnecting peers. Therefore, the D1 and D2 gigabit 5 interface must also be configured with the identical timers. Okay, now you can see neighbor down. This is D1 and neighbor down. This is D3. That timer expired. Verify that the timers have changed on gigabit 001 using show IP OSPF interface command. Okay. Show IP OSPF interface gigabit 001. Show IP OSPF interface gigabit 001. Okay, the hello is 5 and that is 20. Configure D1 with the identical hello and dead interval timers on gigabit 5. Okay. You configure it gigabit 001 on R1. Now configure gigabit 105 on D1. Configure terminal. Interface gigabit 105. IP OSPF hello interval 5 and that interval 20 and okay, R1 is full. It's very good. On R1 go and T1 is full. Okay, and verify. Show IP OSPF interface on D1. Show IP OSPF interface gigabit 105. Okay, hello 5, that's 20. Notice the first OSPF adjacency change message indicated that D1 had lost adjacency with R1. After the commands are entered, the next OSPF adjacency change message indicates that the adjacency with R1 has been re-established. However, the second adjacency change message indicates that the adjacency with D2 has been lost because its timers are not matching. Okay, configure D2 and verify. D2 configure terminal interface gigabit 105. Okay, this interface 105. Enter IP OSPF hello-interval 5 that interval 20 and okay, D1 full, R1 full. Verify and show IP OSPF interface gigabit 105 hello 5.20. Okay, very nice. Now DR and BDR placement. You will configure OSPF DR and BDR placement on the multi-access network. By default, an OSPF router tries to establish neighbor adjacencies with all other OSPF routers. This is a concern with large multi-access networks. For instance, 10 routers interconnected to the same layer 2 switch would require a total of 45 adjacencies to be established. This can cause excessive OSPF traffic and waste router resources. For this reason, OSPF routers interconnected to the same multi-access network elect a designated router DR and a backup designated router BDR. All non-DR and BDR routers are referred to as DR others and only form adjacencies with DR and BDR routers. This reduces the total number of adjacencies and improves network operations. DR and BDR are automatically elected during the last phase of the two-way OSPF neighbor state, before the X start state. DR and BDR elections are conducted as follows. An OSPF router interface with a priority greater than 0 attempts to become BDR on the link. If no BDR exists, then it elects itself the BDR. If there is a tie with another router, the highest router ID is used. If there is no DR, the BDR promotes itself as DR. The neighbor with the next highest priority is selected BDR. The DR and BDR are the central focal points on multi-access network. In a large network, it is advantageous to choose which router should be the DR and BDR. When all OSPF routers have the same OSPF priority, The election is based on the higher router ID. Altering router ID to choose DR-BDR routers may not be convenient. A better alternative is to alter the interface priority. By default, all OSPF routers on a multi-access network have a priority of 1 assigned. An interface priority can be changed using the IP OSPF priority configuration command. The value can be between 0 and 255. Setting the value to 0 ensures the router will never become a DR or BDR. Setting the value greater than the default value of 1 makes a router a candidate to become the DR or BDR. Note, it may be necessary to use the clear IP OSPF process to ensure the proper devices are elected. Verify the current DR and BDR selection. In the topology, R1, D1, and D2 are interconnected on the same Ethernet network. Therefore, a DR-BDR election has already transpired. The easiest way to determine the interface role is by viewing the OSPF interface with the showIP OSPF neighbor command. On R1, verify the current DR-BDR status using the showIP OSPF neighbor command. Okay, showIP OSPF neighbor on R1. Okay, go to R1. Show IP OSPF neighbor. Enter. Okay, D1 is the BDR and D2 is the DR. Okay, this may vary. Don't worry if in your case is different. In my case, D1 is BDR and D2 is DR. Verify the current status of R1. Show IP OSPF interface gigabit 001. Show IP OSPF interface gigabit 001. Okay, this is the DR other. Okay, in my case, R1 is DR other. The designated router is D2 and backup designated router is D1. Verify D1 and D2. Okay, go to D1, show IP OSPF neighbor. R1 is DR other, D2 the DR. Okay, and copy this D2, enter. D1 is backup designated router, BDR, and R1 is DR other. Very good. Change DR and BDR selection. It is sometimes advantageous to choose which router is selected as DR and BDR. For example, we will change the DR and BDR assignment as follows. R1 should be the DR using a priority of 255, the maximum value. D1 should be the BDR using the default priority of 1. D2 never become DR or BDR using a priority of 0. Okay, starting on D2, Enter interface gigabit 5 and set the priority to 0. Okay, go to D2, configure terminal interface gigabit 105. IP OSPF priority 0. Enter. And notice the OSPF message. The reason is because D1 just assume either the DR or BDR role and has established an adjacency with D2. Okay, adjacency with R1, in this case R1. Verify, show IP OSPF neighbor. Okay, on D2, show IP OSPF neighbor. Okay, now D1 is DR and R1 is BDR. Verify, show IP OSPF interface gigabit 105. Now the state is DR other. Now D2 is DR other. D1 is the DR and R1 is the BDR. Okay, now configure R1 with priority 255, the highest priority, to ensure R1 will be the DR. Okay, go to R1, configure terminal interface gigabit 001, IP OSPF priority 255, and okay, and verify. Show IP OSPF interface. And show IP OSPF neighbor. Okay, show IP OSPF interface gigabit 001. Okay. The state is BDR. The DR is D1. The BDR is R1. Show IP OSPF neighbor. Show IP OSPF neighbor, enter. D1 is the DR. D2, DR other. Okay, but remember, it may be necessary to use clear IP OSPF process to ensure the proper devices are elected. Okay, go to R1, clear IP OSPF process. Enter yes. Go to D1, clear IP OSPF process. Yes. Enter. D2, clear IP OSPF process. Enter yes. Now go to R1, show IP OSPF interface gigabit 001. Now R1 is the designated router with priority 255. The designated router or DR is R1 as expected. Backup designated router is D1. The VDR is D1. Very nice. Show IP OSPF neighbors. So D1 is the VDR and D2 DR other. Okay, also you can go to D1, show IP OSPF neighbor. R1 is the DR, D2 DR other, and show IP OSPF interface gigabit 105. D1 is the VDR with priority of 1. And go to D2, show IP OSPF interface gigabit 105. So D2 is DR other with priority of 0. Okay, thank you very much.